We're firing a cannonball that has a mass of 5 kilograms, an initial velocity of 35 meters per second. It's going up in the air 45 meters, and once it's at 45 meters, we want to know how fast it's going. That's basically the premises of what's going on, okay? So let's think about some of the equations we learned yesterday. We learned that work is equal to force times a distance, right? Now, if we wanted to be using something we're familiar with instead of an S, since this is going up, what would we put here? We can replace that S, with a Y. Look at that. That's cool, right? Now, what's another equation that we derived for work yesterday? That it's equal to the change in what? Look at your notes. That'd be cool.
Change in kinetic energy.
Yeah, the change in kinetic energy, which means 1/2 mv final squared minus 1/2 mv naught squared. So, what might we want to use to find VF? Yeah, let's try out this change in kinetic energy. Okay, but is that going to be the only thing we use?
No.
No, we've got to use this one first, don't we?
Yeah.
Why?
Why?
Because we have to know what we're setting this equal to, don't we?
Can you not separate those two?
Okay, I mean, technically you can, but you still have to have it set equal to work. And if you have it set equal to work, then work is unknown and final velocity is unknown, and you have two unknowns, and what are you supposed to do? See? Okay. So before we use this one, which will get its time, we're going to actually want to use this one. So you guys, if something's getting fired straight up and we're solving for its force is mass times acceleration, right? What's the acceleration here? Gravity, okay? And remember, is it going to be positive or negative?
Negative.
Negative, because it's working to bring it down, okay? And then and then we're going to have the delta y, okay? So that means we're going to say negative 5 kilograms times 9.8 meters per second squared times our delta y of 45 meters. So let me know what our work is. Did you say 2 joules?
Yeah.
That's wrong.
2,205.
2,200 and what?
That's a little high. That's 2,205. Or negative.
Let me know if you guys agree with them.
I do. I agree.
2,205?
I agree.
What are the units?
Joules.
Joules. Okay. Now that we found that, can we solve for VF?
Yes.
Yes, we can. Awesome. So we're going to say that work is equal to 1/2 mvf squared minus 1/2 mv naught squared, and we need to rearrange for that final velocity. So what are we going to do? What do we move? Add the
thing that needs to be added.
What's the thing that needs to be added?
1/2 mv naught squared.
Yeah, we're going to add the 1/2 mv naught squared to both sides. Okay, now what do we do?
Divide and multiply.
Multiply by 2, okay? That's going to become 2w plus mv naught squared equals mv final squared. What do we do now? Divide by m, and then what's our final step?
Take the square root.
Take the square root. Awesome. So we're going to have the square root of 2 times negative 2,205 plus our mass of 5 kilograms times our velocity of 35 meters per second all over our mass of 5 kilograms. Oh, and don't forget to square that 35 meters per second too. Or else you're going to be told that it can't do it because you'd get an imaginary number.
So,
What's what?
but,
A negative number under the radical?
that's fine.
You guys have learned about imaginary numbers, right?
Yeah, long time.
Okay.
18.5. That's the
You got what?
18.5 here.
What are the units?
Meters per second.
Ta-da! Not bad, right? Pretty easy.
Wait,
What?
no, I just haven't loaded yet.
Okay, well, I'm going to start erasing now so we can go to the next part.
Oh, man.
We're not firing a cannonball anymore.
Is it 18.5?
Yeah, good job. Okay. So let's talk about work a little bit more. If something speeds up, do you think the work is positive or negative? Positive. If it slows down,
Negative.
what if it stays the same?
Cost 0.
0. There's no work done if it stays the same, right?
Is friction work?
Friction is work. Friction is negative work.
Okay.
Because it's opposing motion. So positive work works in the same direction as motion. Negative work works against the direction of motion.
So if there's a positive work and then there's a friction work, will that equal like 0 work overall?
Well, only if the friction is causing it to not move. Because remember, things can still move with friction, can't they?
Yeah.
Yeah, so you're obviously still doing more positive work than you would be negative work if you're still moving. Does that make sense?
Yeah.
Yeah? Okay. So, something to think about then, since we're talking about work. If a force is perpendicular to the displacement of the object, what do you think work is equal to? Do you think it's positive, negative, or 0? It's going to be 0. Huh?
Because it would be moving in the
It's not moving in the direction of the force. Yeah, so it's going to be 0. It doesn't change the particle's speed, okay? The energy is not changing, so that means no work is done. So whenever we have a force perpendicular to displacement, that means we're not doing work on the object.
how could it be perpendicular?
Okay, so this is my Kindle case, okay? I'm holding it, right?
Yeah.
How am I applying force to it?
Applying
From the bottom, so it's going up, right?
Yeah.
Am I doing work on the Kindle case?
Yeah.
No,
No. Not perfectly.
because I'm going, the displacement of it is horizontal, but the force is vertical. But am I doing work to it now? Yeah, now work will be being done to it because it's moving in the direction of the force.
Okay.
Right? It's pretty cool. So what about if we have multiple forces? What do you think is going to happen if we have a bunch of forces? Yeah, you're going to have to add them all together, right? So if, let's say, we've got this object right here, and we've got force 1 and force 2, force 3, force 4. We've got all these different forces acting on it. Okay? We're going to need to find the overall energy of the system. Okay? And that means that we need to figure out what the total kinetic energy of the system is, which means that we're going to have to add up all of the separate kinetic energies. In order to find our work. Okay. So that change in kinetic energy is going to be the total work of the system. So you have to add all your forces together. So kinetic energy 1 plus 2 plus 3. So every time you know that we've done anything, we start out with the basic equation, right? Then we talk about the change in it, and then we talk about totaling it. And does that formula really ever change of how we do that? No, you just add them all together, right? It makes life pretty simple. Now, the other thing we have to consider is what if there's angles? Okay, what if there are angles? So we know that work is equal to the integral from an initial position to a final position of Fs ds, right? We talked about that yesterday. Well, when there's an angle involved, it's the exact same thing, except now we have cosine of theta involved. So every single time, you guys, that we have an angle, we're going to be able to use cosine, okay? So what it's going to look like when you derive it, well, how about you guys walk me through? Do you remember how we took the integral yesterday? What do you think would be constants that we could pull to the outside of this right side equation?
Cosine theta.
Yeah, we're going to pull out Fs and cosine. And then we're left with ds, right? So what does the ds become? You guys remember what it turned into?
Acceleration.
No.
Velocity.
No. We talked about it yesterday. We said every time you have something like this, would be it goes to just s, yeah. And we're having to evaluate that from its initial to its final, right? So you end up with Fs cosine of theta s final minus s initial, which then becomes Fs cosine of theta delta s. And that is our equation for work whenever there is an angle. So consider this work equation 3. We have that work is the force times the change in distance, so the displacement. We have that it's equal to the change in kinetic energy. And now whenever you know that it's an angle involved, it's equal to the force cosine of the angle times our displacement. And we should have just enough time to do an example with this. Yes, sir?
When you write out this equation, what's the difference between the squiggly line and the straight line?
So between this and this? Is that what you're asking? Okay. So this is saying that you're still taking the integral of this. So after you've taken the integral, this sign, this straight line, means it's evaluated from the initial to the final. So it means evaluated from once you get down there. All right. Where are you guys in AP Calculus right now? Like, what are you doing? You just started what?
Wait a minute, I have.
She's disappointed in us.
Okay. Okay.
Yeah, she yells at us.
You know, so, did she really? Yeah, I didn't think so.
I did
Yeah.
We're going to talk about pulling a suitcase. This is near and dear to my heart because the thing that I was like the most excited to register for when I got married was a suitcase that has little wheels on it.
Suitcase license.
Oh, and it's one of the ones that, you know, you can like, the wheels like turn 360 so you can do like cool things with it.
Oh, wow.
Yeah, because we have to fly a lot because like his mom lives in South Dakota and we don't want to drive every time. So
What's South Dakota?
we've got a strap inclined upward at a 45-degree angle. Oh, you want to know what's really funny though? You guys know where we pass every time we're driving into Yankton? There's actually a town in South Dakota called Wakanda.
Really?
Yeah.
We're pretty close there.
Huh?
All right, boys, we're gonna go to
There's actually a Wakanda. Okay? And we're pulling it through the airport. We're gonna pull it a total distance of 100 meters. Okay? The tension in this strap is 20 newtons. And we want to know how much work does the tension force do on the suitcase. And to give you guys an idea of what this imagery looks like.
You gonna put the spinning wheels on it?
Yeah, I am.
Oh, man. So everyone just-
And we're pulling it from here to here. 100 meters. Okay, so this is what's going on. We're pulling it to the right. Okay, how are we going to solve for the work, you guys? It's really straightforward.
You find the
Work
X
equals what?
component or tension.
Force times
Times
Cosine.
data.
You guys literally just learned this like a few seconds ago. Okay, do we have to rearrange this at all?
No.
No, okay, so tell me what the work is.
20.
Wrong.
Oh, okay. I thought you asked for the
The work. I want the work.
Is it 1,414?
That's what I got.
I got
1,000 what?
414.2.
Bam! Look at you guys. Good job. Okay, we have another example. Let's see if we can do it in 8 minutes. I think we can.
What was the answer? 14.
Okay, so we've had so much fun, you guys. Okay, we launched a cannon. We pulled a suitcase. That was the most exciting, in my opinion. And now we're gonna launch a rocket. Okay, a real rocket, not a model rocket. Right? So the mass of our rocket is 150,000 kilograms.
It's a V2 rocket.
150,000 kilograms, okay? And it's getting launched straight up. The rocket motors generate a thrust of 4 times 10 to the 6 newtons. You guys, there's actually a thrust force this time. I don't know if you remember correctly or not, but there was one time when I was asking you what force it was, and you just kept on insisting that it was thrust, even though it wasn't thrust. We want to know what the rocket speed is after it's gone 500 meters.
Are we gonna do 2-dimensional versions of this?
Who knows? Only I know. What do you think its initial velocity is?
0.
Okay, and just so we can have like an image of what's going on here.
What's the V final?
That's what we're trying to find, yeah. Got a rocket
I know.
that's going.
We'll draw one more. I'll just have it by one. On the paper.
It's actually not CPM. That's what it is.
Okay, this is sort of what's going on, all right? So a little rocket going up. Now, how are we going to solve this?
The equation.
Which equation?
W equals, force. That looks like a man with a Viking hat with a beard.
It sort of does, you're right. Huh. You guys want to use that one? That's what Lance said.
I don't think you're right.
What's another one that we know?
Uh,
We might use this one. We might also use with it the kinetic energy one.
1/2 MTS.
Okay. So where do we want to start? Which one do we want to start with?
I think we should start with the first one.
I think you're right. I think we should start with the first one because we have a force and we have a displacement. So how about you guys multiply those together for me and tell me what the work is? Do 4 times 10 to the 6 newtons times 500 meters. Please give it to me in scientific notation. I do not want to write all the zeros or all the numbers even. I just don't want to do it.
This way. I'm gonna beat Lance to it.
Wait, hold on.
That's the only thing that you're having. 1, 2, 3.
Yeah, 2 times 10 to the
What are the units? Joules. That's a really long line for that J. Okay. Is that what we wanted to find?
No.
No. What do we want to find?
The speed.
Yeah, so we're going to say that work is equal to 1/2 mvf squared minus 1/2 m v naught squared. And we've got some good news. What up here is equal to 0?
Max.
No, it's not the mass. It's v naught, which makes which of these 0?
The right one.
Bam, there we go. Okay, so if we have that work is equal to 1/2 m vf squared, what do we do to rearrange for vf? Multiply by 2, then
Divide by m and take the square root.
I think it has.
all right, tell me what our final velocity is.
163.3 meters per second.
What'd you get?
163.3 meters per second.
Is that what everybody got?
I got that.
I'll put it. Oh, you gotta.
I'll let it slide this time.
I'll let it slide this time.
Yeah, I got that.
I want to say more.
There's something that you guys forgot to take into account. Gravity.
Uh-oh.
What?
Rookie mistake.
What?
Oh, okay.
Oh.
So this,
So it's
Teachers
52.
please dismissal of it.
oh man,
You're bad.
this is just the work due to thrust. You need to find the work due to gravity,
And then
which will be
subtract it.
negative, and then add them together, and then use that total work to solve for the final velocity. So your homework this weekend is to finish this problem.
I need to